Why aren't you falling right now? I mean, you could be watching this video while skydiving, or maybe you've tripped at the exact moment. But recall in the previous video, Mr. Duck was distinctly falling, but I was right next to him and I wasn't falling. So what's the difference? Why am I not in free fall right now? Well, this may be obvious to most people, but it's worth pointing out. So I'm laying on the ground. Whoa, crazy! And you're likely standing on the ground or resting on something that is as well, so you aren't falling either. So these are just wild discoveries today. Okay, let's talk about the act of standing on the ground, how that prevents you from falling through it using the language of forces. And trust me, we will have something to talk about, so let's just get into it. Howdy everyone, I'm Biscuit, and when you're in contact with the surface, including the floor, or maybe just a wall, as you're pushing up against it, it pushes back. So that's actually Newton's third law of motion. Some people define it as every action should have an equal and opposite reaction. We should be much more specific. What we mean by an action, we mean a force. So force is a fundamental unit to move an object. Meaning to accelerate something, you must exert a force on it. That's a little foreshadowing to the second law of motion, but we'll get to that in a minute, so just hold your horses for a bit. But going back to the third law, we can better define it as whenever we exert a force on something, it will exert a force back that's equal in magnitude, but opposite in direction. Now we can most obviously feel this with solid objects like walls, as they're able to resist you moving through. I mean, that's how they stop you, by pushing back as hard as you push. But otherwise you can move through it with no problem. You know, kind of like a piece of paper, which is, it's hard to stay in contact with. It's just so easy to push away. We can also see the third law of motion with rocket propulsion. The idea is if you throw something away, you exert a force on it so it moves away from you, then it pushes you back and propels you in the opposite direction. So you could propel yourself in space by having a large bag of rocks and just throwing them in the opposite direction of where you want to move. So let's take this and get back to our original question. So why aren't you falling? Okay, let's take a look at Mr. Duck here. We know that the table is exerting an upward force on him as he presses down into it. We call this the normal force because it points normal to the plane of the table, or normal speech, 90 degrees or perpendicular in each direction here. But there's also another force acting down on him as well. So gravity is pulling him down. So to figure out how he really moves in the end, we need to use Newton's second law of motion, which states that the sum of the forces on an object equals its mass times its acceleration. So I want to explicitly state that F equals ma is not Newton's second law. Every time I hear that, I die a little bit on the inside. No, you can have one acceleration be moving in one distinct direction, but you can have many forces acting on you. So we need this formulation, we add everything together. So Newton's second law is incredibly important, because if you can write down all the forces on an object, all it's experiencing, we can write down its acceleration and solve the resulting differential equation to figure out how it's actually moving. You know, kind of like in the last video. It's almost like the things I talk about are kind of all related. So let's write down all the forces here just explicitly.
We can say that the sum of the gravitational force and the normal force must equal his mass times its acceleration. Now, whenever you write down vectors, you nearly always need to break them into components, but luckily here, everything is happening vertically, so there's only one component in the vertical direction, so we can just effectively get rid of the vector symbols here. Okay, let's choose up to be positive so that the normal force is positive and the force of gravity is negative. Now, sometimes when doing these problems, you actually already know how your object is accelerating. Not always, but in this case, Mr. Duck is stationary on the table, meaning he isn't moving, he isn't falling, which is the premise of the video, meaning he's definitely not accelerating vertically, so we can just set A equals to 0. This tells us that the two forces must be equal and opposite in direction, essentially canceling each other out. We should note these aren't equal and opposite due to Newton's third law. That has to do with the forces of the table and Mr. Duck on each other, but just happen to be equal and opposite in this case.
At the end of the day, why aren't you falling through the ground right now? Well, it's because the floor is pushing up on you just as hard as gravity's pulling you down, leaving you just there, just hanging out. We're likely not going to be finished using these laws of motion quite yet, especially the second one, so just keep them in mind moving forward. Okay. Thanks everyone so much for watching. Really appreciate it. Thanks, bye.
But I don't know why people say that I look like Bowser